It is not acceptable to splice branch circuits in the main electrical panel to extend them to an emergency generator panel. Splicing branch circuits in the main electrical panel violates the National Electrical Code. Section 300.15 states that splices shall not be located within any panel board or controller. Splices in a panel board can create a fire hazard or shock hazard if they are not properly insulated and enclosed. Splices can introduce resistance and voltage drop, which can degrade the performance of the branch circuits. If a spliced branch circuit needs to be repaired or replaced, it can be difficult to access and work on it within the panel board. The proper way to extend branch circuits to an emergency generator panel is to firstly, run new conduit from the main electrical panel to the generator panel. Secondly, pull new wires through the conduit. Thirdly, terminate the new wires in the generator panel. And fourthly, remove the existing branch circuits from the main electrical panel and connect them to the new wires in the generator panel. Ensure that the generator panel has sufficient capacity to handle the load of the extended branch circuits. Install a transfer switch to prevent backfeeding from the generator into the main electrical panel. Consult with a qualified electrician to ensure compliance with all applicable codes and safety standards. The NEC, or National Electrical Code, is a comprehensive set of standards and guidelines for electrical installations. It's developed and updated by the National Fire Protection Association, or NFPA, and is widely adopted throughout the United States. It aims to ensure electrical safety for people and property. Article 300 covers general requirements for wiring methods and materials. Section 300.15 specifically addresses boxes, conduit bodies, or fittings where conductors are spliced or terminated. The key takeaway is that splices and terminations should be contained within approved enclosures, and panel boards are generally not considered suitable enclosures for splicing branch circuits. Splicing within a panel board creates several potential safety hazards. Poorly made splices can loosen over time, leading to arcing and potential fires. The confined space within a panel board makes it difficult to properly insulate splices, increasing the risk of electric shock. Overcrowding the panel board with splices can also hinder the proper dissipation of heat, potentially leading to overheating and insulation breakdown. Splicing adds resistance to the circuit, causing a voltage drop. This voltage drop can negatively impact the performance of connected equipment, causing lights to dim or motors to run inefficiently. A poor connection can also generate heat, further exacerbating the problem. Accessing and repairing spliced branch circuits within a panel board can be challenging. The limited space and presence of other energized components increase the risk of accidental contact and injury. Troubleshooting becomes more difficult as it is hard to trace the wires to their termination points. Instead of splicing, the preferred method is to extend the circuit using a dedicated raceway, such as conduit, from the main panel to the generator panel. Then pull new conductors through the conduit to create a continuous, unbroken circuit path. The new conductors are terminated at both the main panel and the generator panel. Ensure the generator panel is adequately sized to handle the additional load of the extended branch circuits. This involves calculating the total amperage of all connected devices and ensuring that the panel's busbar rating and overcurrent protection are sufficient. A transfer switch prevents the generator from feeding power back into the utility grid during an outage. This is crucial for the safety of utility workers and prevents damage to the electrical system. Automatic transfer switches are often used for seamless transitions between utility and generator power. Engage a licensed and qualified electrician for any electrical work, especially when dealing with panel boards and generator systems. An electrician can ensure that the installation complies with all applicable codes and safety standards. They also have the necessary tools, equipment, and expertise to perform the work safely and correctly. In the context of electrical systems, a branch circuit is a circuit that extends from the final overcurrent protection device, such as a circuit breaker or fuse, to the outlets, lights, or other electrical loads it supplies. It is a crucial part of the overall electrical distribution system within a building. The National Electrical Code, specifically Article 100, defines a branch circuit as the circuit conductors between the final overcurrent protective device protecting the circuit and the outlets. Several types of branch circuits exist, each designed for specific applications and load requirements. A general-purpose branch circuit supplies power to a combination of lighting and appliance outlets. These circuits typically serve multiple rooms or areas within a building. An appliance branch circuit supplies power to one or more specific appliances, such as refrigerators, washing machines, or dryers. These circuits are often dedicated to a single appliance to ensure adequate power and prevent overloading. An individual branch circuit supplies power to only one piece of equipment. For example, a dedicated circuit for a large air conditioner or a commercial oven. The size of the conductors used in a branch circuit is determined by the load it will carry. The NEC provides tables and guidelines for selecting the appropriate conductor size based on the amperage rating of the circuit. For example, a 15-ohm circuit typically uses number 14 American wire gauge copper wire, while a 20-amp circuit typically uses number 12 American wire gauge copper wire. Overcurrent protection devices, such as circuit breakers or fuses, are essential for protecting branch circuits from overloads and short circuits. These devices are designed to trip and interrupt the flow of electricity if the current exceeds the circuit's rating. The NEC specifies the maximum overcurrent protection rating for different sizes of branch circuits. For example, a 15-amp circuit requires a 15-amp circuit breaker or fuse, while a 20-amp circuit requires a 20-amp circuit breaker or fuse. Outlets are the points on a branch circuit where electrical power is drawn to supply various loads. These can include receptacles for plugging in appliances, lighting fixtures, or other electrical equipment. The NEC specifies the number of outlets that can be connected to a single branch circuit. This limit is based on the total load and the need to prevent overloading. For example, a general-purpose 15-amp branch circuit is typically limited to a maximum of 10 outlets. When extending branch circuits, it's essential to maintain the integrity and safety of the original circuit. This means using the same type and size of conductors, ensuring proper connections, and providing adequate overcurrent protection. It's also crucial to avoid overloading the circuit by adding too many loads. To determine the load on a branch circuit, calculate the total amperage drawn by all connected devices. Add up the wattage of all lights and appliances connected to the circuit. Divide the total wattage by the voltage of the circuit to determine the amperage. Ensure that the total amperage does not exceed the circuit's rating. For example, on a 120-volt circuit, a 1000 watts appliance draws approximately 8.3 amps. When working with electrical circuits, always follow safe work practices. Turn off the power to the circuit before making any connections or repairs. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, consult a qualified electrician. Splicing is the process of joining two or more electrical conductors together to create a continuous electrical path. While splicing is a common practice in electrical work, it must be done correctly to ensure safety and reliability. Poorly made splices can create a fire hazard or shock hazard. Several different methods are used for splicing electrical conductors, each with its own advantages and disadvantages. Wire connectors, also known as wire nuts, are commonly used for splicing conductors in residential and commercial applications. These connectors provide a secure and insulated connection. Crimped connectors use a crimping tool to mechanically join two or more conductors together. These connectors are often used in high vibration environments where a more secure connection is needed. Soldered connections involve joining conductors together using solder. Soldering provides a strong and reliable connection, but it requires more skill and time than other methods. Regardless of the splicing method used, it's essential to follow some basic guidelines to ensure a safe and reliable connection. Always use connectors or splicing methods that are approved for the type and size of conductors being joined. Strip the insulation from the conductors carefully to avoid nicking or damaging the wire. Twist the conductors together tightly before applying the connector or solder. Make sure the connection is mechanically sound and will not come loose over time. Insulate the splice thoroughly to prevent short circuits or electric shock. When working with electrical panels, it's crucial to understand the different components and their functions. The main circuit breaker is the primary overcurrent protection device for the entire panel. It's designed to trip and interrupt the flow of electricity if the total load exceeds the panel's rating. Branch circuit breakers protect individual branch circuits from overloads and short circuits. These breakers are typically rated for 15 amps, 20 amps, or 30 amps, depending on the size of the branch circuit. The neutral bus bar is a conductive bar that provides a common connection point for the neutral conductors in the electrical system. The ground bus bar is a conductive bar that provides a common connection point for the grounding conductors in the electrical system. The NEC provides specific requirements for grounding electrical panels and equipment to ensure safety. Grounding helps to prevent electric shock by providing a low impedance path for fault current to flow back to the source. This causes the overcurrent protection device to trip and interrupt the flow of electricity. When working with electrical panels, it's essential to follow all safety precautions. Always turn off the power to the panel before making any connections or repairs. Use insulated tools and wear appropriate personal protective equipment. Never work on a panel that is wet or damp. If you are not comfortable working with electrical panels, consult a qualified electrician. An emergency generator panel is a separate electrical panel that is designed to provide power to essential circuits during a power outage. This panel is typically connected to a generator that automatically starts up when the utility power fails. Emergency generator panels are commonly used in hospitals, nursing homes, data centers, and other facilities where a continuous power supply is critical. The generator panel typically has a transfer switch that automatically switches the load from the utility power to the generator power when a power outage occurs. This ensures a seamless transition and prevents any interruption in power supply. The size of the generator panel is determined by the total load it will carry. The panel must have sufficient capacity to handle all of the essential circuits that are connected to it. When installing an emergency generator panel, it's essential to follow all applicable codes and safety standards. The panel must be properly grounded and wired to ensure safe and reliable operation. A qualified electrician should be consulted to ensure that the installation meets all requirements. A transfer switch is a device that switches the load from one power source to another. In the case of an emergency generator system, the transfer switch switches the load from the utility power to the generator power when a power outage occurs. Two main types of transfer switches exist: manual and automatic. A manual transfer switch requires a person to manually switch the load from one power source to another. An automatic transfer switch automatically switches the load from one power source to another when a power outage occurs. Automatic transfer switches are more convenient and reliable than manual transfer switches, but they are also more expensive. Transfer switches are essential for preventing backfeeding from the generator into the utility grid during a power outage. Backfeeding can be dangerous and can damage the electrical system. The NEC requires that all emergency generator systems have a transfer switch to prevent backfeeding. When selecting a transfer switch, it's essential to choose one that is rated for the size of the generator and the load it will carry. The transfer switch must also be compatible with the type of generator being used. A qualified electrician should be consulted to ensure that the transfer switch is properly installed and wired. In New Hampshire, electrical work is regulated by the New Hampshire Office of Professional Licensure and Certification. Electricians are required to be licensed to perform electrical work in the state. The licensing requirements include education, experience, and passing an examination. The purpose of licensing is to ensure that electricians have the necessary knowledge and skills to perform electrical work safely and competently. The New Hampshire Electrical Code is based on the National Electrical Code. All electrical work in the state must comply with the New Hampshire Electrical Code. Permits are required for most electrical work in New Hampshire. The permit process ensures that the work is inspected and meets the requirements of the electrical code. Inspections are performed by licensed electrical inspectors. The New Hampshire Office of Professional Licensure and Certification investigates complaints against licensed electricians. If an electrician is found to have violated the electrical code or engaged in unethical conduct, disciplinary action may be taken. The disciplinary action may include suspension or revocation of the electrician's license. When hiring an electrician in New Hampshire, it's essential to verify that they are properly licensed. You can check the status of an electrician's license on the New Hampshire Office of Professional Licensure and Certification website. It's also a good idea to get multiple bids from different electricians before hiring one. Check references and read reviews to get an idea of the electrician's reputation. Make sure the electrician is insured and bonded. Get a written contract that outlines the scope of work, the price, and the payment terms.